In this video, we're continuing section 6.4 on solving trig equations. So we are going to look at some examples where we solve trig equations where we either have to simplify our equation a bit or factor it. Okay, so let's look at an example. So I have the equation 3 sine x equals root 3 times cosine x. Okay, so to get this one started, I'm going to try to move all the trig functions to one side. So I am going to take this cosine x term and move it to the other side by dividing it. So that'll give me sine x over cosine x. And I'm also going to take this 3 and divide it over to the other side. So that gives me root 3 over 3 on the right. And the reason why I did that is now when I have sine x over cosine x, well, that simplifies very nicely. That is just tangent x. So we have tangent x equals root 3 over 3. Okay. All right. So we're going to need to figure out when this happens. When does tangent of x equal root 3 over 3? Okay. So to answer that, I'm going to go to my unit circle. So I'm going to go to my unit circle. So let's draw our axes. Let's draw our circle. Let us draw our circle. Okay. And I know tangent in the unit circle, I know that tangent is equal to y over x. Okay, and this is where we may need to, recall our unit circle from before. Okay, so if I flip it up to my unit circle from before, I'm looking for spaces where y over x will be equal to root 3 divided by 3. Okay, so if I flip it up to my unit circle, flip it up to the unit circle, a little too far. Okay, so where is that going to happen? Where, if I take the y value divided by the x value, where is it going to be equal to root 3 over 3? Okay, so I'm going to take a closer look at, the possible places where it might happen are places like, where root 3 is showing up, like here or here. Okay. The other thing I have to be mindful of is this equaled a positive number. It equaled root 3 over, that was a positive value. And when I divide y by x, for that to be positive, the only quadrants that could happen is in this first quadrant or the third quadrant, because in the third quadrant, if I take a negative divided by a negative, it'll become positive. So I might have to, play around with it and think about, is it going to be points like this or going to be points like that? So now if I flip it back to where we were in our problem, let's identify what point it's at. Okay, let's flip it back to where we are in our problem. Okay, so it turns out that the point that's going to work, there's 2 points. There's one over here, where the coordinates are x is root 3 over 2 and y is 1/2. And the angle there is pi over 6. Pi over 6. And we'll verify that that's the case. And there's one symmetric angle over here, 7 pi over 6, where the coordinates, x is now negative root 3 over 2, and y is negative 1/2. But let's verify it. If I actually do y divided by x, does it actually equal this? So let's test it out. So if I take this point, for example, and I do y divided by x, my y value is 1/2, divided by x is root 3 over 2. So when I divide these, when I divide 1/2 by root 3 over 2, I'll have to multiply by the reciprocal of this. When I do that, the 2's will cancel, and I'll end up with 1 over root 3. Okay, so you might be looking at that and thinking, wait, that looks different from root 3 over 3. But if we rationalize the denominator, as we typically do with the unit circle, I would multiply the top and the bottom by root 3 over root 3. And that gives me root 3 over 3. So that is, in fact, the same as what I have in my equation. If I did the same thing for the coordinates here, I'd get the same thing. The negatives will cancel out, and I'll get root 3 over 3. Okay, so these points are the ones I'm looking for. Okay, so for my answer, I'm ready to say what my answer is. My angle x. Well, there's two possibilities. I am getting pi over 6. I'm also getting 7 pi over 6. But notice that there's no restriction in this problem. There's no restriction, like it's not saying that, my angle is between 0 and 2 pi or anything like that. And that means I could go around the unit circle as many times as we want, and we've seen that to indicate that with our answers, we got to put that plus 2 pi k. And then comma for the next answer, again, plus 2 pi k. That indicates I can go around the unit circle as many times as we want. Comma, and I'm going to say k is an integer. The shorthand way to write that is we say k is an element of, and the symbol for integers is z, with an extra vertical line on that diagonal. That just means integer. Right, that was a symbol we saw way back on at the beginning in week 1 of our class. Okay. All right, so here we have our answers. All right. So just because it's really close to the edge, let me just scooch this up a little bit. One of the things that I want to point out about this is, in this problem, I divided both sides by a variable because I divided cosine x over to the other side. In this problem, it was okay to divide by a variable since nothing canceled. Nothing canceled when I divided that over. So why was that important again? So remember when we saw equations like x squared equals 4x? I'm going to tackle this in 2 ways. First, I'm going to do this wrong. I'm going to do it an incorrect way. And the incorrect way is to divide both sides. Divide both sides by x. Divide by x. Because if I divide by x, on the left-hand side, I'll get x. On the other side, I'll get 4. On the other side, I get 4. But when I do that, I lose an answer. Because if I look at this original equation, I notice that, wait, if I plug in 0 for the x's, that should work. Okay, so here we lose an answer. So what was the correct way of doing this? So the correct way, anytime I'm tempted to divide both sides by a variable, I want to move all the terms to one side to make the other side equal 0. And then I want to factor. So I could take out an x and be left with x minus 4 equals 0. And from there, I know that x equals 0 and x could be equal to 4. So now I'm getting both of the answers. So this was the correct, this was the correct answer over here. So I'm going to put a little thought bubble around this. Okay, so one of the reasons why we ended up losing an answer when we divided both sides by x was, well, when you divide both sides by x, well, what if this thing that you're dividing by ended up being 0? And that ended up being precisely the answer that we lost. Okay, that's why we weren't able to divide both sides by the x. In our problem, we did divide both sides by a variable, by this cosine x. And the reason, the reason why that ended up being okay is because in this problem, it didn't end up canceling away. Whereas with x squared equals 4x, well, it did cancel away. And that cancellation led to me losing an answer. Okay. All right, let's take a look at another example. All right, so let's flip it to this one on the next page. So I got some cosines. I got a couple of tangents here. Okay, so how can I get this one started? Maybe I'll move this square root 3 term to the other side. Let's get one side equal to 0. So I get cosine x times tangent x plus root 3 tangent x minus cosine x. I'm moving that root 3 over, so I'll get minus root 3 equals 0. Okay, so now if I look at this equation, how many terms do I have? So remember, when things are being multiplied, that's considered one term. So this is one term, this is term 2, this is term 3, and that's term 4. So we have 4 terms here. We have 4 terms, and our strategy when we have 4 terms was try grouping. We are going to try grouping. Okay, all right, so grouping coming back into the fold here. Okay, so we can't forget how that works. So I'm going to try maybe grouping the first 2 terms and the last 2 terms together. And in the first 2 terms, I notice that they have tan x in common. So I can factor that out. And then that leaves me with cosine x plus root 3. In the last 2 terms, well, I could take out a negative, and then that'll leave me with cosine x plus root 3, and this equals 0. Oh, and now that's nice because in my 2 groups, I do see a common factor. They both have cosine x plus root 3 as a common factor. So I get to take that common factor and factor it out. So I will factor out that cosine x plus root 3. That common factor, I pull it out to the front. Take that common factor out to the front. And when I do that, I start a parentheses and I write my leftovers. So from group 1, what's left over is tangent x. From group 2, what's left over is technically there's a 1 here. So there's a minus 1. Minus 1 left over. And I got this equals 0. Okay, so now I got it factored. It equals 0. So either the thing from the first parentheses is 0, or the thing from the second parentheses equals 0. So from the first parentheses, that gives me that cosine x would have to be equal to negative root 3. Or from the second parentheses, I would get that tangent x would have to be equal to 1. Okay, so let's tackle these. So when is cosine x equal to negative root 3? So first I want to notice something about this number and about how big it is. So I know square root of 3 is between which two nice square roots? I know it's bigger than square root of 1, and it's smaller than square root of 4. And, well, square root of 1 is just equal to 1. Square root of 4 is equal to 2. So that means square root of 3 is 1 point something. So in my equation that I'm dealing with, I got this negative square root of 3, which is negative 1 point something. Negative 1 point something. But one of the things that we've seen about both cosine and sine is they always, no matter what the angle we plug into them, their output, the number that we get out, is always between negative 1 and positive 1. So this number that I'm getting out is too small. It's smaller than negative 1. As a result, there is no solution since cosine x, well, cosine x is always in between. It's always in between negative 1 and positive 1. But this value, this output, is too small. It's smaller than even negative 1. So I'm not going to get an answer to that. Okay, all right. So I still got one more equation to consider. I also need to think about when is tangent of x equal to 1? So this can happen. So I go to my unit circle. So I draw my axes, draw my circle. Okay, if we already kind of recognized what angles worked here, I might not need to draw the unit circle. I'm just drawing it for additional practice every time we do one of these. So at which spots in the unit circle, when I do tangent, because remember tangent is equal to y over x. So if I think back to my unit circle, at which spots, at which angles on the unit circle, when I divide y by x, does it equal 1? Well, there's two spots. It happens at pi over 4, where the coordinates are root 2 over 2, comma, root 2 over 2. And it also happens at 5 pi over 4. At 5 pi over 4, where the coordinates are negative root 2 over 2, comma, negative root 2 over 2. Right? At both of these, if I take the y value and divide it by the x value, it'll end up equaling 1, because they're just the same. Okay, so I'm ready to say what my answer is, what my angle could be. So the angle, which we're calling x, well, there's two possibilities. I got pi over 4. I'm also getting 5 pi over 4. Do I need to do that plus 2 pi k thing that we had to in the last problem? Well, if I look at my equation, there's no restriction on what the angle could be. Like it doesn't say that my angle is between 0 and 2 pi or anything like that. So we can go around the unit circle as many times as we want. And because of that, we do need to write that plus 2 pi k. So I got to write that here and got to write that here, plus 2 pi k, comma, and I have to say k is an integer. So let me use my shorthand notation. K is an element of z. Remember, z means the integers. All right. So if the problem had given me an interval for x, like if x was in the interval from 0 to 2 pi or something like that, then I would only be going around the unit circle one time, and then we would only get the answers pi over 4 and 5 pi over 4. We wouldn't put plus 2 pi k on them. All right. All right, so let's end this video by taking a look at one more example. One last example in this video. Okay, so for this one, I got sine x minus 3/2. This is cosecant x equals 1/2. So for this one, I want to have you pause the video and try this one on your own first. Often, getting these equations started is the hardest part. So I want to give you an opportunity here to think about how you might get this one started. So pause the video for 3 minutes to try this one. Pause it in 4, 3, 2, 1. Pause it, and try this one on your own first. All right, so hopefully you did that. Hopefully you paused it and tried it on your own. Let's talk about it. So one of the things I'm going to notice is cosecant x is the reciprocal of sine x. So if I use that fact, I got sine x minus 3/2, and then cosecant x is the same thing as writing 1 over sine x. 1 over sine x. And this whole thing equals 1/2. Okay. And why that's nice is now instead of me seeing two different trig functions in the problem, I only see one trig function in the problem. Like I'm seeing a sine x here. Oops, sorry. I am seeing, let me highlight in different color, sine x here, and I see another sine x here. So let me try substituting for it. Let me try substituting. I'll pick a new variable like u, and I'll let u be sine x. Okay. And when I substitute, I get u minus 3/2 times 1 over u equals 1/2. So I substitute and we get this. All right, so I got u minus, and when I multiply my fractions together, this is 3 divided by 2u equals 1/2. Okay, so it's looking simpler than what I had before. At least the trig part of it is out of the way. Now this is more like an equation that we saw back in, what was this, week 2 or week 3 of our class, back in when we talked about solving equations in section 1.5, I think. Okay, so, well, I don't love the fact that they're fractions here. So to get rid of the fractions, why don't we multiply both sides? What would we need to multiply both sides by to get rid of both of the denominators? Well, I would need to multiply by 2u. That would get rid of this denominator, and it'll also get rid of the other denominator on the other side. So when I do that, on the left, I will distribute 2u to each of these terms. So doing that, I'll get 2u squared for the first part, and then when it's distributed to the fraction, it'll get rid of that. It'll cancel that denominator. So I get minus 3. On the other side, the 2's are going to cancel, and that leaves me with u. All right, so I can move all the terms to one side. I get 2u squared minus u minus 3 equals 0. Okay, so I got a quadratic. You know, the leading coefficient is not 1. So I could either do this by splitting the middle, or I could do it by trial and error. As we're getting towards the tail end of the class, we really want to be getting more and more comfortable with trial and error, especially when we get to calculus. There's just going to be more of an expectation that to factor these quadratics, we are pretty comfortable doing it by trial and error. So at this point, I want to give you a quick, maybe 1 to 2 minutes. 1 to 2 minutes to try to factor this by trial and error, especially if you're used to usually doing it by splitting the middle. I really challenge you to try this thing by trial and error. So pause it in 4, 3, 2, 1. Pause it and try to factor this. All right, so let's talk about it now. Okay, so these first two terms, well, they got to multiply to 2u squared. The only options are really 2u and then u. The last two terms, they got to multiply to -3. But I can't just pick whatever I want, because I have to pick these terms in such a way that when I FOIL it out, the outer terms and the inner terms, they'll combine to make this -u. And that's where the trial and error comes into play. I may have to try a few things, but it turns out that what works is doing -3 here and then +1 there. Okay, so now I got it factored. So from the first parentheses, I get u equals, what do I get? 3/2. From the next parentheses, I get -1. Okay, so that's what u equals, but I substituted, so I got to plug these back into my substitution for the u. So that gives me either sine x equals 3/2 or sine x equals -1, or sine x equals -1. So one of these has no solution automatically. Because remember, sine x, whatever the value that I get out as the output has to be between -1 and +1. But 3/2, that's not in that range. It's not in between -1 and +1. So this equation right here has no solution. No solution since sine x needs to be between -1 and +1. But 3/2 is bigger than 1. So that has no solution. So that's nice. That's a little bit less work for us. And then, well, for this one, it equals -1. That is an output that is allowed for sine. So that one will have a solution. So if I think about my unit circle, where on the unit circle is sine equal to -1? And we know in the unit circle that sine is equal to the y-coordinate. Where is the y-coordinate equal to -1? Well, it happens at the bottom, at the angle 3 pi over 2. Because at that angle, the coordinates are 0, -1. And sine is my y value, and the y value there is -1. Okay, so the angle that works, this angle that works for us, it's x, my angle x, is we get 3 pi over 2. And there was no restriction on the angle in this problem, so we can go around the unit circle as many times as we want. So I do have to write my plus 2 pi k. Okay, comma, where k is an element of z. That means k is an integer. And there we have it. There is our answer. Okay, so one of the takeaways I want to have from this example is sometimes when I'm solving an equation, a trig equation, sometimes it's helpful to rewrite functions, to rewrite some of our trig functions in terms of sine or in terms of cosine. Like cosecant x, for example, is 1 over sine x, or secant x is 1 over cosine x. I don't always need to do that, but occasionally it can be helpful like this.